But today we want to look at acids and bases. And I've highlighted some in both chapter 14 and chapter 15 review documents. So I better mark. This group is from chapter 14. Ready to roll?
I think so.
Okay. All right, let's take a look at this first one. Which of the following is a conjugate acid-base pair? Remember, a conjugate acid-base pair, this is number one. If we just take a generic acid, its conjugate base is going to be that. And to be a conjugate acid-base pair, you have to have two things. These parts have to match, and you can only lose one hydrogen. So if we had this one, then it would have to be that. Okay, so if we take that as our definition and look at our options, first one's got an oxygen in it in the conjugate base, can't have that. Second one has lost two hydrogens, can't have that. Third one puts a twist on it. Okay, we do have the NH3 from this part, and we've lost one hydrogen. So that's a valid acid-base pair. We've introduced ammonia in terms of this reaction, right? NH plus OH minus. But if you flip that around, then this becomes the acid because it donates a proton to the hydroxyl. So we're actually looking at this from the other side. But it does meet the definition. And D can't be it because it's lost two hydrogens also. And E can't be it because there's only one valid one. All right. Number two. The hydrogen sulfate or bisulfate ion. Hydrogen sulfate is the proper IUPAC name for this. Bisulfate is a trivial name. It's archaic, but it's still used lots of times in commercial products. They'll still refer to it as bisulfate. It can act as either an acid or a base in water solution. In which of the following does it act as an acid? If this is going to act as an acid, and let's write out the complete chemical equation. It's not abbreviated. It would have to react with water. And if it's an acid, it has to lose a proton, transfer a proton to that water molecule. So we would have this left over and hydronium as a product also. So D is the only one that fits that description. Now, if it were going to act as a base, what would it do? Well, more than likely, we would go back to the first dissociation. That would give us that product. It would act actually it would act as an acid there also. Oh, if it were to act as a base, we would have to transfer a proton from water to that. And that's highly unlikely because sulfuric acid is a very strong acid for its first proton. So it wouldn't act as a base. All right, 3. Which of the following is the equilibrium constant expression for the dissociation of weak acid, HOCl? Okay, so let's see, 3. So we need the balanced equation. And this is an aqueous solution. This is a pure liquid. All right, and we get OCl minus in aqueous solution plus H3O plus. So the K for this acid would be OCl minus hydronium and then HOCl only, because we don't put pure liquids in here. Let's see. A is a good one for that. Oh, okay. They're using a simplified version. So instead of writing it this way, we would eliminate the water and this would be a hydrogen ion. Mathematically, it works the same. There's no difference. Chemically, it is different because this never happens. But we use it because it's more convenient. All right. How about number 6? Okay, a solution in which the pOH is 12.1. pOH 12.1 is given, would be described as acidic or basic or neutral. All right. Well, you could gain the skill of seeing that as acidic, but it's easier for me to convert it to pH. I have an intuition with pH. So this would be 14 minus 12.1. Let's see, that'd be 1.9 pH. Okay, so that's very acidic. Let's see, 7. Which of the following indicates the most basic solution? Okay. In that case, we've got to take each one and try to convert them into some apples form. So we don't have apples and oranges and pomegranates all mixed together. So the first one is 1 times 10 to the minus 10 is hydrogen ions. 10 to the minus 10. The pH here would be 10. Right? pOH is 6.7 for the next one. 6.7. So its pH would be 7.3. And C, hydroxide ion concentration is 7 times 10 to the minus 5. H. 7 times 10 to the minus 5. So pOH would be equal to negative log 7 exponent 5 log, change sign. That would be 4.2, and pH would be 9.8, right? Okay, and then D is pH 4.2. And the last one is at least 2 of the solutions are equally basic. Equally basic. Well, if they're equally basic, they'd have to have the same pH. None of them have the same pH. So it's not that one. And the most basic. This one right here. pH 10. Seems like the simplest answers require the most work. 8. Right. Which of the following solutions contains the strongest acid? All right. To be the strongest acid, it needs to have the lowest K value. And if we're going for, if there's more than one hydrogen available, we don't have to concern ourselves with the second K, because the pH is going to be controlled by the first K, especially if they're 4 or 5 orders of magnitude difference. And that's the case for B, right? The second K is 10 to the minus 12, first K is 10 to the minus 5. So we don't have to concern ourselves with the second K. We just need to compare the Ks for each one of the above. And first thing I would do is look at the exponents. Right? The smallest exponent, and if there are any that are equally small, then we go to the tiebreaker, which would be the coefficient. But in this case, 10 to the minus 4 for HF, right? 10 to the minus 4 is the strongest acid out of that group. If we didn't have that one, say we had another one that was, say, 10 to the minus 7, then we would go to B and C, and then we need a tiebreaker. And that would be C, because 1.8 is less than 7.9. Excuse me. No, I got that backwards. We want the largest K. It would be B. Yeah, 7.9 is greater than 1.8. If we didn't have E to deal with, then we break the tie with B and C with the coefficient. All right. Oh, strongest conjugate base. I threw that one in there just for giggles. The strongest conjugate base would be the weakest acid. And the weakest acid in there is A, 10 to the minus 10. So the weakest conjugate base would be that one right there. Oh, excuse me. Strongest conjugate base would be the, yeah, that's right. I checked myself. Number 9. Which of the following statements are true? Okay. First one says, pH of a strong acid is always lower than the pH of a weak acid. Okay. Strong acids and weak acids are based upon their K values. Those are intensive properties. The pH is based upon concentration. Well, that's also an intensive property. But the concentration can vary. So much so that the strong acid can be such a low concentration that its pH is greater than the pH of the weak acid. Okay. So that's false. We used to keep a stock concentrated acids, and we'd make up our solutions with them. One of them was glacial acetic acid. It's acetic acid 100%. It was a very heavy bottle. It's pretty dense. But acetic acid is a weak acid. But I dare you to stick your finger in that bottle. It will eat it off with that concentration. Okay, B. Let's see. The pH of a solution can never be negative. I think I showed you that one in class. All you need is hydrogen ion concentration of, say, 1 molar, and that pH would be -1. So all you have to do is find one that doesn't meet that description, and it's false. And it's false because pH is simply a mathematical transform. Okay, for a conjugate acid-base pair, Ka equals 1 over Kb. True or false? Nope. No. What is Ka? Ka equals Kw over Kb. So this is false as written. At least two of the statements are true. False because the last one, all the statements are false. That's true. All right. We'll skip one there and go to 11. For the stepwise dissociation of aqueous H3PO4, which of the following is not a conjugate acid-base pair? All right, so we could go through the whole thing. If we lose one proton, right, that gives us H2PO4 minus. Again, if we lose the second proton, that gives us HPO4 2 minus. And if we lose the third proton, that's PO4 3 minus. So those are your valid acid-base pairs for phosphoric acid. Let's see, which of the following is not a conjugate acid-base pair? Okay, so let's see, H2PO4 minus for the first one, that's not, right? Wait a minute. No, that's true. That's true. This one. Yeah, first one's true. Second one, that one's true. C, that one's true. D, nope, lost 2 protons. It went from here to here. All right, so D is wrong. And why did I throw in H3O, the hydronium ion? Because it's going on at the same time in aqueous solution. But it's true. So D is the bad one. Number 12. Let's see. For which of the following 0.1 molar diprotic acids would the second dissociation affect the pH significantly? What we need to do is compare the powers of 10 for the first K and the second K. The first K, there are 5 orders of magnitude difference, right? Right, so there's no effect from the second one. B, -4 and -8, that's 4 orders of magnitude. Second one has no influence. C, -4 and -9, 5 orders of magnitude, no influence. D, -3 and 9.3 times 10 to the -4, which is almost 1. So they're very, very close together. I would expect second one to have influence. Right. Now, don't ask me for an example because I don't know any acids that do that. This is a made-up problem. All right, 16. All right, which of the following would give the highest pH when dissolved in water to form a 0.1 molar solution? The highest pH, 0.1 molar. We want the highest pH. That is the most basic. Strong acid, nope. Weak acid, nope. Okay, so we're going to C, D, and E. We're looking at salts there. Potassium salt of a weak acid. Potassium salt. A potassium salt of a strong acid would be what? Well, like KCl. This would have been derived from KOH. This would have been from HCl. Strong acid, strong base gives you a neutral solution. And so that would be it. But strong base, weak acid gives you a basic solution. So a good candidate is C. We haven't looked at the last one yet. Ammonium salt of a strong acid. Ammonia is a weak base. With a strong acid would be an acidic solution. So C is your best answer. Number 19. Solid ammonium acetate. Let's see. Wait a minute. There's more to. There it is. Based upon that statement, select the answer that best describes an aqueous solution made from each of the following substances. Okay. So we're going down to 19. Ammonium acetate. So the Ka for ammonium is 10 to the minus 10. 5.6 times 10 to the minus 10. The Kb for the conjugate base of acetic acid is the same number. That's a neutral solution, right? Nobody wins in that case. So C is the best answer for that. All right. Oh, here's another one based on the same situation. Okay, in this case, number 20, we've got ammonium perchlorate. Let's see. HClO4, ammonium perchlorate. Okay, the acid part of this molecule is 10 to the minus 10, Ka. And the Kb for this one is about 10 to the minus 21. Kb, right? Ka wins. Right? So this is going to be an acidic solution. Mm-hmm. 22. That's getting a little weak. Which factor listed below is most important in determining the strength of an oxyacid? Remember, an oxyacid has at least one proton, and then it has something else here. We'll just call it X. And then it has oxygens, however many. That's a generic form of an oxyacid. The single most important factor for the strength of the acid is the number of oxygens. Because usually you have this here and you have that there attached to the oxygen. And if we add more, let's see, if we do like that, then what you get is by induction, we draw electron density away from this bond right here. And that weakens the bond by pulling electrons away because oxygen is so electronegative. And usually X is a halogen. So we're weakening this bond, and that's why perchloric acid is extremely strong acid. It's not only that, it's a very strong oxidizing agent. We used to use it in the lab to destroy organic material of our plant samples so that we could get at the ash or the mineral content. But we had to be careful with it because if you take perchloric acid, concentrated perchloric was 70%. If you take say 20 mils of that and a pat of butter, and you put it in your tall beaker and set it on the hot plate and turn the heat on, pull the sash down and evacuate the building because it will blow. So what we used to do is overnight, we'd treat our samples with nitric acid first. And then the next day we'd hit it with perchloric and heat it up, and perfectly safe. Okay, so that was 22, 24. Oh, not too good either. Got one of these old ones. Which of the following species below, when dissolved in water, will not produce a basic solution? Okay. So, let's see. A, B, C, D, E, right? Will A produce a basic solution? No. Non-metal oxides in water produce acidic solutions. So we'll take this one as our example. We dissolve it in water. Then we get a proton transfer. This becomes the acid, and that's the base. We get a proton transfer over here. And we get the whole molecule. We end up with H2SO3. Sulfurous acid. So that one's a good answer. That one does not produce a basic solution. Ammonia always does. Metal oxides, when they react with water, they produce hydroxides. Like that. Let's see. 2 hydrogens, 2 oxygens. Yeah, that's right. They produce basic solutions, and barium hydroxide is already there. So this is basic, acidic. Doesn't produce a basic. All right. Up to this point, we've been talking about acids and bases in terms of Bronsted-Lowry. Now we're going to look at Lewis. A Lewis base is an electron pair donor. Lewis base versus an acid. This is electron pair donor. And this is an electron pair acceptor. So 25. Which of the following species cannot act as a Lewis base? All right. We need the one that has no available electrons. This one, it's got electrons out the wazoo, right? This one, right, it has all those lone pair electrons. This one, methane, has no free electrons. Right? That would not work as a Lewis base. H2S, it's got 2 lone pairs. And then ammonia has 1 lone pair. So all those other ones are perfectly good as Lewis bases. Let's see, 26. Which of these cannot act as a Lewis base? All right. Well, using the same logic, you see there that you've got if you see negative charge, you can assume it can act as a Lewis base. And so N3 minus, NH2 minus, NH2 minus, NH2 minus. NH3 still has its lone pair, but NH4 has hydrogens like this, and like that, with no lone pairs, right? It doesn't have any lone pairs available. So that would not act as a Lewis base. How about 27, Lewis acid? Which one cannot accept a lone pair? Well, potassium can. It's positive charge. Magnesium, aluminum, all three of those, they're looking for electrons because they're positively charged. Hydrogen ion, right? It'll accept electrons. That H minus, it's got all the minuses it can handle. It's already got a lone pair. That's what gives it the negative charge. It's not going to accept another lone pair. Well, that's why E is the answer for that one also. I'm not sure why I crossed this one out. We'll move on. The reason is lost in time. Okay, are we still talking? No. Can't remove this. It's out of the way. All right, number 30. Okay. Dig into my haversack. Given the following pKa's, which is the weakest base of the answers listed? Okay. The temptation is to look at the pKa's and find the strongest acid makes the weakest base, right? So we would tend to go toward HClO2. HClO2, and its conjugate base would be ClO2 minus. Right? But we snuck one in there on you. Chloride. That is a strong acid. This is going to be the weakest base. Okay, I think that's why I marked this one, because of that trick. Temptation would be to answer A. If you don't see the chloride answer down there. Because the Ka for HCl is virtually infinity. Let's see, how about skip down to 38. Carbonic acid is a diprotic acid, H2CO3. All right. Every time you take a sip of pop, you're downing carbonic acid. H2CO3. And it has two Ka's. Ka1, Ka2. And I'm going to put those values up here, 4.2, 10 to the minus 7. 2 times 7 and 4.8, 10 minus 11. Oops, 8. 10 minus 11. At 25. The ion product for water is 1 times 10 to the minus 14. So Kw, and I don't even have to write water out here because Kw always means the K for water. Okay. What's the OH concentration of a solution that is 0.1 molar in sodium carbonate? 0.1 molar sodium carbonate, right? Put in carbonate. Oops. Yeah. um, all right. So in aqueous solution, this one is going to produce this reaction, and I'm going to abbreviate. One proton there, and then HCO minus, and then HCO3 minus. Lose another proton, CO3 minus. Okay. So when we put this in solution, what do we get? We get 2. And this is completely soluble. So we get 2 of these and 1 of those. Okay. So initially we're starting off with 0.1 molar right here. 0.1 molar. There. Excuse me. So, I feel like I'm barking at the wrong tree. I do that sometimes. Okay, that's right. Wait a minute. I wrote that down wrong, didn't I? 1.8. Okay. Okay. All right. That's why I put that hint there. If we calculate the KB, since we're coming from the other direction, then the reaction is going to be in the other direction. It's going to be CO3 2 minus and water HCO3 minus plus OH minus. And the initial concentration here is 0.18 molar. That's a 0, and this is essentially 0. So the change is going to move that direction. Okay. We're going to have plus X here, and minus X there. So at equilibrium, this one, now, which one controls the reaction? This one's going to have the largest KB because this is the strongest base. So we really only have to calculate KB for this one. Let's see, KB for the second one is 10 to the minus 14, and then 4.8 times 10 to the minus 12. And that'll give us the KB for this reaction. And I'm going to preserve 2 decimal places to avoid rounding error. Oops, not 14, 4. So that's the one that's active here. Minus X, this is X, this is X. So our 2.08 times 10 to the minus 4 is going to equal X squared over 0.18 minus X. All right. I'm going to make an assumption that that's approximately X squared over 0.18. I'm going to say that this value is so small that compared to 0.18, because this is 10 to the minus 4. That's going to be so small that we can do that approximation. So I'm going to take this value times 0.18 and then take the square root of it. And that should give me x equals 6.12 times 10 to the minus 3. Now, what was the question? What's the hydroxide ion concentration? 6.1 times 10 to the minus 3 is A. Now, we will get some influenced by this equation, but this KB is going to be so small, it's going to be a similar 4 orders of magnitude difference. So the KB from this one is not going to influence the pH. It's not going to influence the hydroxide ion concentration. Now, what would the pH of this solution be? I mean, while we're here, that would be, this is the hydroxide ion concentration. So I'm going to take the negative log, 2.21, and then subtract it from 14. So the pH would be 11.8. And the rule of thumb says strong base, weak acid, we're going to get a basic solution. So that's confirms. All right. $39. What's the pH at equivalence for the following titration? So we got 0.1 molar hypochlorous acid, 0.1 molar hypochlorous acid. Oops. There we go. Excuse me. And the pK for this is, oh, the Ka, excuse me, Ka for this equals 3.5 times 10 to the minus 8. Okay. And we're titrating with 0.1 molar sodium hydroxide. 0.1 molar sodium hydroxide. Okay. If we neutralize, this is neutralizing the acid. When you put the same amount of hydroxyls in here as hydrogen ions, which you have, then we've neutralized it. So then what we get is we've got this reaction available because we've neutralized those hydrogens. We've freed up this conjugate base. So the conjugate base is now free to react with water and produce that. Okay. So what we're doing is we're going to completion first, right? The stoichiometry. The stoichiometry tells us that we have 0.1. Well, actually, it's not that because we have equal volumes of each. So it's 0.1 molar. Actually, we could just pick a volume. That'd be the easiest way. Just say we use 100 mils of each. 100 mils of each. then that means we've used 10. We end up with 10 millimolar per 200 mils, right? Initially. Once we neutralize it, then we get this left over, but it's diluted by another 100 mils. Okay. We've used up the hydroxyl, so there are no hydroxyls in there. And we've used up all the acid. So this is equal to what's 1/20th? 0.05 molar. Is that right? 1/10 would be 0.1, 1/20th would be 0.05. Yeah. This is 0, and this is 0. So the change we're going to get is moving that direction. We're going to lose some of this. It's going to show up over here. And at equilibrium, we're going to have 0.050 molar minus X, and then X and X. So what we need is the KB. So the KB for the hypochlorite ion is 10 to the minus 14 divided by that value. That's a negative. This is 2.86 times 10 to the minus 7. Okay, so now we can write 2.86 times 10 to the minus 7 is equal to x squared over 0.050 minus x, which is approximately x squared over 0.050. Because that value's, this k is so small. So I would multiply this times 0.05 and take the square root of it. So what was the question? Calculate the pH. Okay. So X equals 1.2 is pretty close. 1.2 times 10 to the minus 4. Are you with me so far? Okay. And that's equal to the hydroxide ion concentration at equivalence. So the P of OH is the negative log of that, is 3.9, and the pH is equal to 14 minus that, is 10.1. Is that even close? Yeah. No? Why does it say 7.9? At equivalence. What did I do wrong? Number 39. I got two of them. Oh, that's an error. Yeah, that's an error. It shouldn't be C, it should be E. I better fix that. There we go. Did I include the correct copy of this in your handout? Number 39. Worked problems 39. Well, this is my copy. The key should have the correct answer in it in the bright space. Okay, good. Okay, so I just needed to correct mine. And let me see. Let me save it. So I don't have to do that again. Yeah, the logic here is good. It was 39. Yeah, it wouldn't make much sense to me. If you look at the, what are we forming in that reaction? We're forming that salt, right? This is derived from a strong base. This is from a weak acid, so it should be basic, right? 7.9 doesn't make any sense. That's too close to neutrality. So yeah, 10.1 is the right answer. Oh, okay, so that's chapter 14. We're going to pick it up at chapter 15. Here we go. Well, let's see. We're going to skip those and go down to number 4. So let's change this. Chapter 15. And number 4. Weak acid HF is in solution with dissolved sodium fluoride. Okay. If hydrochloric acid is added, which ion will react with the extra hydrogen ions? Okay, so what we're actually saying is we've got a buffer solution. So the HF is going to be in solution, and I'm going to simplify it. This would produce hydrogen ions and fluoride ions. And the fluoride ions would be placed in solution as a salt of sodium fluoride. And the HF would be as the acid. And if we have 1-to-1, right, same concentration of each, we have a perfect buffered solution. That's not part of the problem, but that's what we would be shooting for. If we add hydrochloric acid to this, what is reacting? Well, that produces hydrogen ions, chloride ions. Right? Chloride's not going to react with water or the hydrogen ions. So when we add this, we focus on this common ion. We're increasing that value, which should shift back this direction. That means it has to react with fluoride ions. Okay. Okay, that was number 4. Number 5. Which of the following is true for a buffered solution? Okay. All right. A, B, C, and D. A says the solution resists changes in hydrogen ion concentration. Yeah, that's true. Solution will not change pH very much, even if a concentrated acid is added. Well, that's true also. The solution will not change its pH very much. Oh, wait a minute. Oh, even if a strong base is added, same thing. It will change some, and it depends on how much you add also. But in general, as long as we don't exceed the buffer capacity, then we won't get a massive change in pH, even if we add a strong acid or a strong base. And then D says any hydrogen ions will react with a conjugate base of a weak acid already in solution. That's generally true. Most buffered solutions are combinations of weak acid and its conjugate base. Now, occasionally we get weak bases in its conjugate acid. But if you flip the equation around, it's going to be, it's going to fit that definition anyway. So all of these are true. Every statement there is true. Okay, how about number 8? How do the pHs of the buffered solutions compare? Let's see. For A, the pH of a buffered solution 1 is greater than that of buffered solution 2. How do the pHs? Oh, wait a minute. I forgot that the conditional statement. You have two buffered solutions. Solution one has 5 molar HOC, that's acetic acid, 5 molar acetic and 5 molar sodium acetate. Right, so we have equal amounts. Buffer one has 5 molar and 5 molar of the acid and its conjugate base. And solution two has what? It's a decreased concentration, 0.05 and 0.05. 0.05 and 0.05 molar for A and B. Okay, so they're both buffered solutions. Right? The ratio of conjugate base to the acid is 1. That makes a good buffer. Okay, pH of the buffered solutions. The pH of buffer solution 1 is greater than that of buffer 2. No. pH is exactly the same. pH of buffer 2 is greater than that of 1. Nope. C, the pH of buffer solution 1 is equal to that of buffer 2. That is true. And cannot be determined as false. And none of the above is false. So they have exactly the same pH. Now, where do they differ? This one will accommodate more acid or more base and hold its pH. It has a higher buffer capacity as compared to this one. 100 times higher buffer capacity. Okay, number 9. Looks like it's a standalone. All right, which of the following is the net ionic equation for reaction that occurs during the titration of nitric acid with potassium hydroxide? What's the net ionic equation for every acid-base reaction? In its abbreviated form. It's the same for every acid-base titration. All we had to do was remove the spectators. Okay, number 10. In the titration of a weak acid with 0.1 molar sodium hydroxide, the stoichiometric point is known to occur at a pH value of approximately 10. Okay. Equivalence. Equivalence at pH 10. Okay, that's given. Which of the following indicator acids would be best to use to mark the endpoint of this titration? Well, you want the one that's closest to that pH, right? It's Ka is going to be is going to tell you if we take the negative log of that Ka, it's going to tell you the pH at which the two forms of the indicator are equal. H indicator, IN. The ratio, that's the wrong ratio. This ratio, that ratio is going to be equal to 1 at the pKa for that acid. And that's where we want to see the change. In fact, the change is going to be plus or minus that value, 1 unit of that value. Well, actually, it's plus or minus more than that one. So, if this is 10, then we want to be able to detect that color change near 10. Okay? And the only one that comes close to that is B, minus 11. So this would be 11 plus or minus 1. So that puts it within the range. That's why B is the best answer for that one. A better choice would be pKa of around 9 or 9.5. Because then by the time it changed to pKa plus 1, it would be closer to that pH. So when you're going from, if you're titrating with a base, you're coming up from underneath, you want the pKa of your indicator to be just below this one. I mean, that'll work, but it would be better if your indicator had a pKa of less than your equivalence point. And that's a physiological influence, the way your eyes respond to color changes. Thirteen. Which of the following solutions would be described as a buffer solution? Okay. Well, first of all, we need an acid and its conjugate base, and this needs to be, actually not weak. This needs to be weak. And we need some ratio here of 1 to 1. That would be the best buffer. So let's look at each one and see which ones have weak acid conjugate base. Okay, first one, no. That's weak acid, strong acid. B, that's weak acid and base. Okay, possible. C, sodium bromide. That's the salt of a strong base and a strong acid, right? That will not work at all. Ammonia plus sodium hydroxide. Possibly. Except that ammonia is already basic. So if you add sodium hydroxide to it, that's not going to give you the conjugate, right? What we need for that one would be this and this, right? And you're not going to get it from that solution, right? Add base to that, it's just going to make it more basic. So that won't work. And then 0.25 hydrochloric and sodium hydroxide, that's strong acid, strong base, that won't work. So B is probably a good answer. Let's see if it works. We've got acetic acid and we add 0.2 molar sodium hydroxide. That's pushing it, right? But it's the best one we have. You're way on the basic end of your buffer zone. So if you add a little bit of base, it's probably not going to hold its pH very well. If you add acid, yeah, it'll work. So when in doubt on a multiple choice test, pick the best answer. Okay, get that out of there. 14? Yeah, 14. 14. Which of the following mixtures would be classified as a buffer solution? Okay. We have a similar problem here. So let's check it out. 50 milliliters of 0.1 HCl and 50, no. Strong acid will not work. B, okay, we got a weak acid. And we've got 55 milliliters of sodium hydroxide has neutralized your acid completely. Right, you're out. You're not in the buffer zone then. That won't work. 50 mils of acetic and 25 mils of sodium hydroxide. So you're only neutralizing half of your acid. That gives you acid and an equal amount of conjugate base. That's perfect right there. D, you don't have enough base, right? You've still got mostly acid and you're not in the buffer zone yet. And then the last one, you're adding two acids together. Okay, so C is your best answer. Let's see here. Scroll down to number 19. Consider the following indicators and their pH ranges. Okay. Assume an indicator works best when the equivalence point of a titration comes in the middle of the indicator range. For which of the following titrations would methyl red be the best indicator? All right, I think this one, I may have gone to extremes with this one, all right, and done it quantitatively. That's what I'm thinking. Well, there might have been a quicker way. All right. Yeah, that might be the only way to do it. It's going to take some time to get it analyzed. We'll take them one at a time. Methyl red, 4.8 to 6.0. Methyl red, 4.8 to 6.0 pH. That's its indicator range. So we want a pH at equivalence of about, let's see, what would that be? 10.8, half of 10.8 is 5.4 at 5.4 pH. That's the middle of the range. Okay, the first one is not going to work. Strong acid, strong base, that's going to neutralize at 7. All right, so A is out. Won't work for that. What we need is something that has an equivalence near in the acidic range. Maybe we can narrow our choices that way. Aniline has a Kb of 10 to the minus 10 with hydrochloric acid. So weak base and strong acid is going to put it in the acid range. Right, so B could be. Ammonia has a Kb of 10 to the minus 5 and hydrochloric acid. So that could possibly be also. All right, D, HF 10 to the minus 4 and sodium hydroxide. So we've got a weak acid and a strong base. That should be in the basic range. So I don't think D is going to work. All right. Yeah, we actually came out with a just above neutrality on that one. And then acetic acid and sodium hydroxide. This is not going to work either because you've got a weak acid and a strong base. So this is going to be in the basic range also. So it's a toss-up between B and C. We'd have to actually do the calculations for those. And let's see if I can do this one quickly. We have a Kb for aniline. Yeah, we have a Kb for aniline. And we don't give you the structure of aniline. We're adding hydrochloric acid. So aniline, let's just abbreviate it like that. Aniline and your hydrochloric acid is going to yield the conjugate acid of the base. And, well, that's abbreviated, so it'll be like that. So what we want is if we're going to use I wonder if we can use Henderson-Hasselbalch on this. It's worth a try. Henderson-Hasselbalch then would work from the acid side. So what we would need to know is if we want the pH, then we need to know the pKa of that plus the log of the base, AN, over the acid. Okay, so we are going to need the pKa. We've got the, let's see, we got the KB, 3.8 times 10 to the minus 10. So the KB equals 3.8 times 10 to the minus 10. Ka is going to be 1 times 10 to the minus 14 over 3.8 times 10. And that's equal to 2.63 times 10 minus 5, and pKa, the negative log of that. That's 4.577. So let's see if this works. 4.5797 log. So what's the AN concentration? Let's see. 0.1 molar. Well, now wait a minute. If we might not be able to do it this way because we're reaching we're at the point where we've got this yielding that plus that. Let's do this like that. Okay. So we need to know these two, this value and that value. All right, we may not be able to use Henderson-Hasselbalch. Shoot. Well, all right, so if we're working from that equation and we've neutralized this one, right, we've gone 0.1 molar and 0.1 molar. So that means this concentration is going to be over here now, and it's half its original. So this is 0.05 molar, right? Because they're equal concentrations of base and acid, and we've neutralized it. So then we're going to have a situation where we got the KB, 3.8 times 10 to the minus 10 equals x squared over 0.05. I did away with the x. So this hydrogen ion concentration is 4.36 times 10 to the minus 6. And negative log of that is 5.36. That's pretty close. Pretty close for pH. This is hydrogen ion concentration. Yeah, I can't use Henderson-Hasselbalch in this case. It's worth a try. We did have to calculate the, no, we didn't, because this is a KB. All right, so we didn't have to do this part. All right, if you're in a hurry on an exam, I'd stick with this one because there are no squirrely ones in there. And if we went to C, 1.8 times 10 to the minus 5 on ammonia, what is that actually going to be? 7.92. No. C. Where did it go? I'm missing a page. Okay. No, 4.63. So it's going to be a lower pH than that. If you find out this is a pH 5.36 with a KB of 10 to the minus 10 and C. And C is KB of 10 to the minus 5. That's going to give you a more acidic one versus 10 to the minus 10. 10 to the minus 5 would be more acidic. So you can settle on that one. You know that the pH at equivalence for C is going to be lower than that. These are the kind of calculations that you would have to do if you don't have a color chart and you don't have any experience with that titration. If you're going to do this titration a lot, then you'll only have to do that calculation once to find out which is the best indicator, and then you go with it. Okay, 23. Time. Okay, we're good. 50 milliliter solution of 0.0350 hydrocyanic acid is titrated with 0.0333 molar solution of sodium hydroxide. What's the pH of the acid solution after 15 mils of titrant have been added? So we're giving you a clue. It's going to be an acidic pH. So look at that again. Oh, 23. Okay. This is the type of problem. This is not going to be equivalence. So we have to actually do stoichiometry situation first, and then take that information to the equilibrium expression. So what's the stoichiometry? Well, we got 50 milliliters of hydrocyanic acid. So hydrocyanic acid. And then we're titrating that with sodium hydroxide. So that's going to give us sodium cyanide plus water. Okay, we're starting off. Our initial situation is 50 milliliters of 0.035 molar. 50 milliliters of 0.035 molar. And sodium hydroxide is titrated with, after 15 milliliters of titrant. This is 15 milliliters of 0.0333 molar, right? Okay. And we're given the Ka 6.2 times 10 minus 10. 6.2 times 10 minus 10. Okay. So we're starting off with this much. This is one of those situations where absolute amounts work best. So initial and then, or before and after. How many moles do we start off with here? Or millimoles? This times that would give you millimoles. So 0.035 times 50 is 1.75 millimoles minus a certain amount, because we're going to use up all of this would be 15 and 0.0333. This would be 0.4995 millimoles. So we're using up, it's a 1-to-1 ratio. So 0.4995 millimoles. So this is 1.25 millimoles of hydrocyanic acid remain. And then this one is 0 afterwards. Okay? That's the stoichiometry part. Now, once we get to this point, we've got some of this and some of that. This right here. So if we set that up, I'm going to try to squeeze it in over here. We've got the cyanide plus water is in equilibrium with hydrocyanic acid plus OH minus. Now that requires a KB. So the KB is going to be 10 to the minus 14 divided by that. .2 minus, that's 1.61 times 10 to the minus 5. That's the K for this reaction, because that's the base. Okay? So what's the initial concentration of cyanide? Well, we had 50 milliliters plus 15 milliliters. So it's millimoles divided by milliliters, which is 65 milliliters, right? I think I did that right. So 1.25 divided by 65 is 1.923 times 10 to the minus 2 molar. 1.923 times 10 to the minus 2 molar. Start here. And we're saying we've used all that up, so we're starting off at 0 here. Right? And we're essentially 0 there also. So the change is going to be in that direction. So we're going to lose something here. It's going to show up over here. And at equilibrium, we have 1.923 times 10 minus 2 minus x, and then x, and then x. So the equation that we solve is 1.61 times 10 to the minus 5 kb, and then we put x times x here, and 1.923 times 10 to the minus 2 minus x here. Now the question is, this is pretty small, but is this small enough? It's 3 orders of magnitude difference. That probably x is probably going to go out. We should be able to solve that equation without the x. I'm looking to see if I did it that way. No, I did the quadratic. Let's do it. Let's estimate this and see if we get the same answer or close to the same answer. Okay, so I'm going to take that value times this value and then take the square root of it. So x equals 5.57 times 10 to the minus 4. And x is hydroxide ion concentration. What's the pH? All right, so if that's x, then the pOH is negative log of that, which is 3.25. And then the pH would be 14 from that, 10.7. Well, that didn't work. Why didn't it work? Let me see what I did wrong. 25, 1.92, 10 to the minus 2. Yep. Oh. That was dumb. That was very dumb. Because um oh, huh. It should have worked. Cyanide ion concentration. We created cyanide, didn't we? Yes, we did. We created cyanide in the amount of this because this neutralized that and produced 0.4 divided by 65. I bet it'll work now. Even though the problem I worked in there was with the acid, and this is I'm going to do it as a base, 0.4995. So this is 7.68 times 10 to the minus 3. Okay. HCN. This one is 1.923 times 10 to the minus 2. And this one is 7.68 times 10 to the minus 3. Now, 7.68 times 10 to the minus 3 minus x. Is it going that way? No, that's large. It's going this way, isn't it? Oh, no, because that's 0. It's got to go that way. Sorry. Just thinking out loud. So this is going to be 1.92 times 10 to the minus 2 plus x, and same thing over here, 1.923 times 10 to the minus 2 plus x. Okay. So we got a different equation down here. All right, KB, 1.61 times 10 to the minus 5 equals 1.923 times 10 to the minus 2 plus x squared over 7.68 times 10 to the minus 3 minus x. Okay. Boy, I dug myself a big hole there, didn't I? Mathematically speaking. Let's see, is there a way we can simplify this? Is x going to change that much? Hmm. Whoa. I don't see any way I can simplify that. Because we can't get rid of x on both of them because there'd be nothing to solve for. If I got rid of this one, then I still have an x squared there. If I got rid of that one, I'll still have an x here. Maybe I could do that. Why don't we get rid of this one? Okay, square that value. 1.923 exponent and square it. Okay. So this one here equals 3.698 times 10 to the minus 4. Okay, so if I take that one and divide it into this one, wait a minute, if I move this over here, 7.68 times 10 to the minus 3 minus x equals, move that over there, This over here, I divide this one into that. Then that equals 22.969. And then, we'll just leave minus X over here, and then this one minus that one, which is really nothing. Yeah. 22.96. That gives me a negative X. All right, this ain't gonna work. Come out with a negative number. All right, so what we have to do then is go back to the acid equilibrium. Like that. I think that's the only way we can solve it. That was the stoichiometry. I should have known better. The stoichiometry is basic. The equilibrium is acidic. Yeah. Okay. So now we know these concentrations. This one left over is 1.92 times 10 to the minus 2. And this one is 7.68 times 10 to the minus 3. Initial. About hydrogen ion concentration. We neutralized the hydrogen ions, so they're essentially zero. Okay, so we're going to move this way, minus this, plus this, plus this. Right? That's why I did the quadratic. Minus X, this is X, and this is 7.68. 10 minus 3 plus X. Okay, so now we're using the Ka. 6.2 times 10 to the minus 2 equals X times 7.68 times 10 to the minus 3 plus X over 1.92 times 10 to the minus 2 minus X. Okay. Now, is X change going to be large? Maybe that's why I did the quadratic, because I wasn't convinced that X would be small enough to miss this. Well, it's 10 to the minus 10. I think X is going to be vanishingly small. So that's why I'm going to say X times 7.68 times 10 to the minus 3 over 1.92 times 10 to the minus 2. We'll see if it works. So that means I got to bring this one over and multiply, bring this one over and divide, and that's our X. 6.2 exponent minus 2, and then 1.92 exponent minus 2 times, and then 7.68 exponent minus 3. Divide. And I get 0.155. Nope. It didn't work. This part was okay, but these didn't work. Okay. So far, that's right. That's right. Oh, you big dummy. Try that again. 1.92 exponent 2 times and then 7.683 divide 1.55 10 to the minus 9. And that is hydrogen ion concentration. So pH equals negative log 8.8. Is that even close to the? Yeah. So we didn't have to do quadratic to solve this one. We just had to recognize these as so small that they wouldn't impact those values. Question?
Yeah. So it's close to B.
Oh, that's not right. It should be 8.81. That's another mistake. It's you probably got it right in yours, don't you? See? This is an old key. The work problems come out as 8.81. I didn't hand you a key to this one. It's in Brightspace.
Okay.
But I did give you the work problems, and the work problems, I believe, are 8.81. I just need to correct my key there. For the next class. And I'm no better than try to do Henderson-Hasselbalch on that first one and basic equilibrium on this one. That's a good rule of thumb. If your stoichiometry is basic, then your equilibrium is going to be acidic when you have to do this type of problem. Okay, 25. I think we're getting close to the end of this one, aren't we? Yeah, 25 is the last one. Okay. All right. 25. A certain indicator has a pKa of 9. Right. So IN. And the pKa for this one equals 9. The color change becomes visible when 7% of this is in that form. All right, so we can use Henderson-Hasselbalch here. If the question is, what's the pH at this color change? So we've got the pKa. What we need is an expression for this one over this one, right? At color change, this has converted into 7%. So the ratio here is going to be 7 over 93, isn't it? Yeah, that's the ratio for this. And this is going to be 9. So that should be an easy calculation. 167, 93 divide, and then take the log of it. And then plus 9. 7.88 pH. Close enough. 7.85. Oh, I know what happened here. I think I know what happened. Yeah. The creators of this question fail to recognize that when it's in 7% is in this form, then what happened to the other? Well, it had to come from somewhere. So if it was 100% to start with, now we've only got 97% left. So the way the authors of this problem solved it was to put 7 here and 100 there, which was wrong. Should have been 93. That's why there's a discrepancy. This would have been a smaller value. Yeah, this would have been bigger. This one would have been smaller. The log of a smaller number makes a smaller negative. Actually, no. The log of a smaller number. Let's see what it would have been if this were 7%, 0.07. Right? Yeah, 0.07. Take the log of that. So that's minus 1.15. That would have been 7.845, 7.5. That would have made this number smaller because this value would have been bigger, been more negative, smaller, but more negative, drove this one down to a smaller value. Yeah. Okay. Any other questions? I didn't ask that at the very beginning. If you had any that you wanted to get to, did we miss any that you were concerned about? Either one of you.
I think I'm good.
How about wait a minute. There's one I think that I missed talking about. Let me look at it's 26 and 27. That's not here. Was it here? Oh, here it is. There's more. I'm sorry. We're not done yet. Okay. The worked problems does not address 26 and 27. So that's why I stuck these in here. So we're using this figure below, right here. And why don't we let's just rough it out. Right. If this is added base, this is pH. And we're going to go, let's see, all the way up to 14. So 2, 4, 6, 8, 10, 12, 14. So we're just below 2 here. And we're going up through 2, 8, 10, 12, 14. We're going up through B is going to occur about right here. Going up like this. And then we're going to go up to about over 8. Like that. Then we're going to flatten out again at around here. And then we're going to go up past 10. And we're going to hit 12 about right here. And 14 like that. So we've got A is here. B is here. This is C. This should be D. Right? Yep. E is here. And that's it. Okay. So what do each one of these places mean? acid, no base added. This is the first buffer pH. It's a little bit above 2. I don't show that too well here. The 2's down here. This is the first equivalence. This is a diprotic acid. Right? So it's going to be like this. And then this. There we go. This is going to have a pKa. This is going to have a pKa. And let's go to the questions now. First one. In this figure below, the pH at first hydrogen equivalence is approximately what? So where's the first hydrogen equivalence? Right there. So let's go down here and read it from a graph that's a little better than this one. C, yeah, is 6. This pH 6. So the first hydrogen equivalence is 6. C. No, that's messed up. Let me be sure I got the questions right. The pH at the first hydrogen equivalence is, no, that's the second hydrogen equivalence. Below at pH at the first. Okay, that's wrong. It should be C. This is really messed up. Okay, this is the first hydrogen equivalence. Second hydrogen equivalence is here. But that's not the question. Acid would best be used in a buffer near pH what? Well, it's either in B or D. Right? So B is about 2.2. This is about 2.2. And D would be about 9.8. Okay. So which one's closest to that? D. D is closest to that. This would be the best buffer of the available answers. Now, if I got sneaky and stuck in maybe a 2.5 or something, then you'd have to go to this one. And I took that one out. What we're trying to do here is to get you to recognize what this titration curve means in terms of the stoichiometries and the buffers. Now we're done.